So I think we can start just on time. So hi everybody, welcome to our presentation. Thanks for being here. We will present today cloud architecture for SIL4 railway applications. My name is Dino Bosnjic. My background is in infrastructure and DevOps, working previously in the trading industry. Currently I work for Hitachi Rail and similar stuff. I'm here today with my colleague Gábor Szitás.
Welcome everybody. We are happy to present you our previous 2 years of job and the current product that we are developing. We had 20 plus years of highly resilient and available systems from all over the previous industries that we are showing you. From Hitachi Rail point of view, you already know that we are in train and metro line businesses, in signaling, and also on locomotive business. Everybody remembering probably the Shinkansen that Hitachi Rail has.
Okay, so at Hitachi Rail, we are committed to provide safe, secure, and highly reliable solutions for the railway operators all around the world. So some of the challenges that we faced while building the latest iteration of our product is, first one is, as always in this industry, we are dealing with the critical infrastructure and safety critical applications, up to 6 nines of availability for the networks and 5 nines for the rest of the system. We have a rigorous cybersecurity requirements, and we are building currently private cloud architecture, meaning that we do not have physically access to the internet. We are also keeping in mind geo-redundancy, and we need to maintain these systems for 20 plus years in production. Also, we need to be compatible with at least 4 decades of railway standards. So, at Hitachi Rail, we are prioritizing always safety and reliability in every step while designing these systems.
So, you can ask how we measure safety. So, safety integrity level defines the required availability for all the subsystems that it has. It has a corresponding tolerable hazard rate, and our job is to minimize any hazard that can happen on the field. For better understanding and to show you some volume of the numbers, that around 22 million people are choosing railway systems in a daily basis within the EU. This is a huge number. You can compare it with planes, it's only 3 million passengers. It's a huge and extreme careful that we need to care. One big aspect that we are not covering any cargo traffic here, only passengers. One important thing that I wanted to show you, that even the SIL numbers are not covering anything for you, and it's not showing you too much. I get some interesting examples for you from field. For example, train doors can be categorized as SIL2, while in metro lines, most of the train doors are automated, which belongs to SIL3. It has a bigger availability and requirement standards. From automotive point of view, all the airbags in all your cars belongs to SIL3. Now you can imagine in our industry, in railway systems, then, for example, 2 TGVs with 300 kilometers per hour going 2 trains against each other in the same train track. It cannot be done. We need to avoid any risk that even it can happen.
So you would also be worried why we chose to go to the cloud systems in general. So historically, applications in the railway were running on the dedicated railway certified hardwares. Recently, railway demands have heavily increased. We have rigorous safety and system approach, which enable us to use modern hardware and software stacks. And we have a couple products which are helping us achieve this move to the cloud. Hitachi Transvital, which platform which enables safe computation and communication, and Hitachi Transverse platform, which enables cloud-native and highly scalable software solutions. Together with all of this stuff, we were able to achieve what we achieved, and we will start showing you our stacks. Gábor?
So we go deeply onto the system. So in high level, get the cookbook that we are cooking in the back. So we are using closed network. Everything is secured. We don't have internet access. We don't want. We're using hardened base Ubuntu systems. On top, that's why we are here. We are using OpenStack. We choose Kyope with Bifrost and Ansible combination to deploy everything together. We are currently on the Bobcat release. We know that soon it's end of support, so we are preparing for the next upgrades in the next couple of months probably. One important aspect that we are using Designate for a DNS as a service heavily. All the upper layers depends on that. All the railway applications require low latency network. We choose OVM, which is directly on Bobcat, but on extra requirements, we are looking towards DPDK. Right now, we already have OVS DPDK. We are moving to OVM with that. From safety reasons, we have integrity measures towards the hardware as well, and we are making sure that everything is on Ceph. On workload point of view, we have mixing microservices with traditional VM workload. Also as a transition from embedded boards to VMs and VMs to microservices. Depends on the characteristics that the application needs. One important thing that I need to show you that we are rack aware. Everything is availability zoned. We are using and choose that concept that one rack is one availability zone. We have minimum 3. Towards the applications, everything is aware of the topology below it. So all the VMs are deployed by anti-affinity rules. So we make sure that the same workload, not running on the same server, not even the same rack. Kubernetes workload, we are populating the data to the workers as topology labels. And for availability, which is the most important for us, on the underlying layer that we choose OpenStack to provide that availability towards all the applications that we have. For microservices, we're using stateful sets and deployments in the minimum 2 or more replicas. For VM kind of workload, we're using the 202 systems, if you know what I mean.
Okay, so on my first slide, I already mentioned that we are dealing with geo-redundancy and geo-redundant systems, but let us first zoom at one physical site to look at the high availability of one site itself. So we have 3 server cabinets and 1 network cabinet. We have a couple more cabinets, but they were mainly there for establishing communications with the railway subsystems. For the context of this presentation, we will just deal with these cabinets on the picture itself. Each one of these cabinets have 2 top-of-the-rack switches and 15 servers. Each server is equipped with 2 network cards with 2 network ports, which are cross-connected with the top-of-the-rack switches. And moving further, these top-of-the-rack switches are cross-connected with the core routers located in the network cabinet itself. Also, we have SSDs in the RAID 1 configuration, 2 SSDs in the RAID 1 configuration for the operating system itself. Logically, from the software aspect, we are of course running OpenStack and Ceph on top of them. Each one of these cabinets have one controller node, 11 worker nodes, and 3 storage nodes. What is important here to say is that we configured OpenStack to have availability zones per rack, which means that when we are running workload on top of OpenStack, we are distributing this workload alongside these availability zones. So in some catastrophic scenario, let's say that entire racks goes down, our safe applications are still safe. From the Ceph and the storage nodes, we have a configuration that we are using replica ×3, which means that every file, every byte is replicated 3 times in each rack itself, just to have our data safe. And yeah, we are using latest generation hardware, of course. Let us now zoom out to the geo-redundancy perspective. We will have in production at least 2 primary sites, which are physically located in different places. Right now it's planned to be about 50 kilometers between each other. Each of these primary sites will have a server room, which I already showed in our previous slide, and the operator room. And we have a backup operator room, which is conveniently located between these 2 primary sites, physically located between these two primary sites. And what is important here to say that we have an independent infrastructure, meaning every one of these primary sites are running separate OpenStack and Ceph instances, and data replications is happening on the application level itself. Every one of the applications running in this physical site is able to connect to the railway stations from both sites itself. So they are connected for both sides. What I did not mention also that between these sites we are using network topology type ring network topology, and everything is end-to-end encrypted. So let us now look at the couple of scenarios which can happen while maintaining or working with these systems in production itself. First of all, let's look at the normal relaxed scenario, which will be day-to-day scenario. So applications which are running in the one physical site are always connected to the railway station located in that physical location itself. Railway operators, represented by these 3 humanoids, are operating from the operator room, and they are operating railway stations for that physical site itself. As my colleague already mentioned, we are using DNS resolution to point correct connections from the operator room to the applications itself. Next scenario which can happen is, Gábor?
Is anything which can happen and we know about it. So if we know about it, that we started to discuss with the customer that how it's affecting the working railway systems. If we figure out that anything is degrading the workload, then we can say that, okay, all the workloads are moving to the other side, while the operators can be still in place. So this is important because we can make any maintenance in operation time, means almost 24/7 in 7 days during the day. How we do it? We DNS failover to the best active site and make the data center on site 1 totally disabled while it's totally up and running. So all the workloads are there, all the servers are there, and we are free to change anything. So even a small failure like replacing disks, replacing multiple servers, changing availability zones, installing new racks, changing electricity, we are covered with that scenario. Because, yes, as I already mentioned, the biggest thing is the availability for the system.
let us now consider the most catastrophic scenario which can happen. Here is represented by the fire at one physical location. First of all, this failover in this kind of scenarios is always manual. So we do not have automation which would trigger this failover to one side, just to avoid any problems which can occur. Secondly, we would shut down all of the network equipment and the servers and all of the load from the affected site, just to avoid any split brain situations which can happen. Then all of the applications would be running on a non-affected site. In the meantime, the client itself can inform that some of the train movements will be limited or stopped, and the passenger informations would be, of course, announced. Also, while everything is happening, what I described, the operators would move from the operator's room from the affected site to the backup operator room, and then they can connect via DNS resolution to the applications and continue monitoring and running the railway stations which they need to do. So, what is most important thing that we need to say regarding our presentation is that we managed to leverage generic off-the-shelf hardware, use open source software, deployed in generic way, and we were able to safely run safety critical SIL4 applications on top of it, which is a big thing. Thank you for your time, and we are open